I am so honored to be here today. I have talked on the subject that I'm about to talk about once before, and I'm proud that I had the chance to do so. It was at the Harvard Divinity School about 6 months ago. I'm writing a book of this title that will come out in April. And the topic that I want to take on is not one topic, it's vast. So I'm going to begin by trying to put it in what I think is a global framework. If you'll allow me, and if you won't allow me, tough luck, I'm standing up here and have the mic. In some form or another, a global civilization is or will emerge. We already have one. We don't think about it as a global civilization yet. It's highly diverse. We do not know what form this civilization will come to be in the coming century or two or three. We don't know whether it will be homogeneous or, I hope, forever diverse and forever inventing new cultural forms on its frontiers, new forms of music, new forms of art, new forms of science, and so on. But we don't know. In the course of the forming of this global civilization, we can, for the first time in human history, thanks to the internet, all talk to one another. This is a unique moment in history when a global civilization is happening and we can talk to one another. We confront problems of enormous scope on a variety of topics that everybody knows about, but I just wanted to mention them because I'm only going to take up one vast subtopic, on these topics. So one of them is that everybody knows is global warming. We will fry ourselves. You going to do something about that, Eric? Thanks. So one is global warming. Another is water resources. A third is the problem of peak oil. I don't know if you've thought about it, but there will be a day where we get the most oil we can out of the earth per day that we ever will. The oil folks up in Calgary, which is the richest governmental unit in the Americas and Europe, it has a $7 billion a year surplus. It's a lot of oil up there. Think peak oil will happen in a couple of years. What this may mean as aggregate demand from India and China and the rest of the world go up and outstrips supply, for industrial society we can only guess. It may be horrendous if we can't get alternative energy resources online fast enough. There are military and political issues that we're all aware of. Part of what I think we can for the first time consider doing is initiate or carry on, because people have already initiated, a global conversation on a variety of topics. I've just named a couple. One of those spaces, which is the one that I want to talk about, is the spiritual. I'm a biologist, doctor, Jewish, non-believing biologist, I guess. I don't believe in God. But I think we need God, and so I'm going to talk about God. So let me begin, having said that, with a poem, which is appropriate, I think, for the Humanities forum, actually. This is written by John Donne, I think you all remember, For Whom the Bell Tolls, in about 1590. Batter my heart, three-personed God. For you as yet but knock, breathe, shine, and seek to mend, that I may rise and stand, or throw me, and bend your force to break, blow, burn, and make me new. I like an usurped town to another do, labor to admit you, but oh, to no end. Reason, your viceroy in me should defend, but is captive and proves weak or untrue. Yet dearly I love you, and would be loved fain. But am betrothed unto your enemy. Divorce me, untie, or break that knot again. Take me to you, imprison me, for I, except you enthrall me, never shall be free, nor ever chaste, except you ravish me. I think this poem is just exquisite. There are some who don't like Donne. I think he's one of the great poets of the English language. He wrote this when he was a high Anglican churchman, shortly after the Church of England came into existence. And if you can't hear the passionate cry of anguish between reason and faith that Donne voices as a high Anglican churchman, then I didn't read it right. So one of the splits that I want to talk about is between, if you will, secular society and the world community of a variety of faiths. There are many people in this room who do not believe in God. There are many people in this world who believe in the Abrahamic God of the Jewish, Christian, and Muslim traditions. If you look at a pie chart of the world's religions, the most abundant is Christian, the next most abundant is Muslim, the next most abundant is those like me who do not believe in an Abrahamic God, or a God at all. We're about, our group number is about 1.1 billion, then Buddhists, and then other wisdom traditions, and then a variety of other traditions. But meanwhile, at the time that we're talking about, in Donne's time, T.S. Eliot, who you all know, wrote, perhaps accurately, that at the time of Donne and the metaphysical poets of the Elizabethan era, for the first time in the Western mind, a split was arising between reason and the rest of human sensibilities. Now, it's only within about 100 years from Donne that we get Newton and his 3 laws of motion and universal gravitation and celestial mechanics, and modern science is born, and the Enlightenment comes along. And one way or another, we're all children of the Enlightenment, and now much of the first world consists of children of the Enlightenment. The humanities, I think it's fair to say, and I think I can almost quote Wendy, who I've just met, but I hope I'm not misquoting you, Wendy, and I hope you don't mind. Roughly speaking, I'm not quoting her now, Christian Book is a friend of mine. He's a Canadian poet up in Calgary. And Christian has written interesting books on how the humanities have bounced off the wall of science for 350 years, adoring it, hating it, despising it, reviling it, rebelling against it, and being romantics and so on. What I want to say is that as much as the schism between reason and faith splits humanity, there are 4 injuries that we all suffer and we don't even know it. But maybe you'll recognize it. The first I've just spoken to. It's the split between the sciences and the humanities. It's the split of which C.P. Snow wrote in the 2 cultures. So I've spoken about that. The second is that the scientific worldview, and I'll speak about this in depth, that we live under, know it or not, is reductionism, which I'll explain in more detail later. But it's roughly the theory that everything is to be accounted for by particles in motion down there, whatever the particles are and the fields are, and I'll talk about that in a bit. In physics, there are only happenings. Balls roll to the bottom of hills. Stars do what they do. Planets go in orbits. There are happenings. There are no values, and there is no doing in physics. So one of the splits that we live with that comes out of and is birthed by reductionism is a split between fact and value. An old mentor of mine, Wolfgang Köhler, one of the early founders of Gestalt psychology, wrote a mid-20th century book entitled The Place of Value in a World of Fact. And, in fact, it was entirely unsuccessful. Nobody paid any attention to it. And it was against this sense of a meaningless universe that the French existentialists like Sartre and Camus said, yes, the universe is meaningless. Isn't it absurd? Where do we find meaning? Well, we valiantly make choices, and that's what brings meaning to our lives. So the continental philosophers have been very aware of this. Anglo-American philosophers have been technical and haven't. I know, I'm trained in Anglo-American philosophy and still know a fair amount of it. The third is that for those of us who don't believe in a God, particularly among us who happen to be scientists, but But among businessmen, jurists, not jurists, but lawyers, judges, people of everyday life who don't believe in a God, many of us have been told that spirituality is just plain foolish, that it's balderdash. Let's get down to the business of business, and what's good for General Motors is good for the country, and let's do it right. So we've been taught that spiritualism and spirituality, not spiritualism, but spirituality is tomfoolery. We really have. Not all of us feel that way. But human beings have been worshiping gods for certainly 10,000 years, maybe 5 million years. Neanderthal buried their dead. Maybe they too worshipped gods. So somewhere deep in us is a cry for a kind of spirituality that found its voice over hundreds of thousands of years in hominid evolution, and certainly the last 10,000 years in gods and spirituality. I think we secular humanists are bereft of it. And the last thing that I want to mention as an injury is we lack a global ethic. For example, we secular humanists, of which I'm one, of course that's an epithet to right-wing Christian fundamentalists. We secular humanists tend to believe in love of family, love of friends, fairness, justice, democracy, and roughly speaking, the free market. After that, that's it. We don't have a sense of a global ethic. Proof of which in part comes from Ken Arrow, who was a friend at the Santa Fe Institute and is one of the best economists in the world. And Ken was asked to evaluate the value of U.S. national parks, and he was stymied because he couldn't calculate the utility of a national park for U.S. consumers. Even in our appreciation of nature, we're reduced to consumers, and everything is commoditized. But the value of national parks, of course, is life itself. And if you don't know that, there's something blind in you. But we don't know how to quantify that. So we lack a global ethic. And part of what I want to say is that finding a sense of the sacred, which is what I'm going to turn in the rest of the talk to, and finding a sense of God that we can share, will be part of our jointly constructing a sense of the sacred, will be part of finding a global ethic, will be part of how we will choose to construct and guide the construction of the global civilization that we're trying to make. So that's the overview. That's what is at stake. In fact, a lot's at stake. Now let me turn to reductionism. So everybody knows Newton, nice fellow. Actually invented, coins have these little fluted edges. Newton invented that. He was head of the mint. And the reason he did it is he came up with the clever idea that if you did that, you could tell if somebody was shaving the coins. It's not celestial mechanics, but it's pretty neat, okay? So with Galileo and Newton, and certainly with Laplace, who I'll tell you more about in a second, what is now known as reductionism became the reigning scientific doctrine that has reigned with complete hegemony for 350 years. So what is it? Well, it's easiest to understand by looking at Laplace. So he was, I guess, in the time of Napoleon. And he said, you know what? If I knew the positions and velocities, or more fancily, the momenta, of all the particles in the universe, right now, I could apply Newton's laws, which are time reversible, forward and backward in time, and I could tell you the entire future evolution of all the particles in the universe, and I could tell you the entire past history of all the particles in the universe, if I had an intelligence of sufficient magnitude. This is called Laplace's demon. He got 4 MacArthur fellowships. I mean, he's a really smart guy. Or she. I actually don't know sex on this one. So that's reductionism. It's the honest-to-gosh view that most scientists are reductionists. There are going to be scientists in this room. We're all reductionists. I'm a reductionist. There's nothing wrong with taking things apart and seeing how they work. But I don't think reductionism is adequate. But let me quote Steven Weinberg, Nobel laureate, who's a modern-day reductionist. And Weinberg says in 2 different books, the more we know of the cosmos, the more meaningless it appears. And perhaps equally importantly, he says, the explanatory arrows always point downwards, he says. He says, if you want to understand a society, you're going to explain it in terms of people. Then you're going to explain people in terms of people parts, for example, organs. Then you're going to explain organs in terms of cells, then cells in terms of biochemistry, then biochemistry in terms of chemistry, again chemistry in terms of physics, and then finally, of course, in terms of particle physics, because he's a particle physicist. And, you can throw in some fields and some general relativity and stuff like that. So that's reductionism. It is the view that at root, there's 2 senses of reductionism. One is epistemological, which is what we can know, and the other is ontological. It's what's real in the universe. So in this Laplacian, Weinbergian view, what's real in the universe is particles in motion, whatever the physicists are telling us is down there right now, like string theory, okay? And everything else is somehow made up out of these things. And the dream used to be that it would be possible to deduce upward from these fundamental laws, Weinberg's dream of a final theory, some neat equation on a t-shirt that would be the union of general relativity and quantum mechanics called quantum gravity, upward to everything, including a couple walking along the Seine in love. I think that view is entirely inadequate, and I'm going to try to convince you of it. But it's the reigning doctrine that we have, and in that view, there's no place for values. So the next step is to tell you that very good physicists have, since about 1970, doubted the adequacy of reductionism. The first who've done so is Nobel laureate Phil Anderson, who wrote an influential paper in 1972 in Scientific American called More is Different. And he begins with the ammonium atom, which is 3 carbons and a nitrogen, making a little tetrahedron. And because of quantum mechanics, if you imagine gluing the 3 carbons down to a table, which is a little tough to do, but imagine you do it, the nitrogen can be above the table or below the table. And it flips back and forth by quantum tunneling really fast. But now if you take a sugar molecule, in principle it can flip back and forth between different conformations, but because it's a lot bigger and more complex, the flipping time turns out to be so slow that it would take vastly long times to flip. So all of a sudden, handedness in molecules emerges. Molecules can be left-handed or right-handed, as was discovered by, oh golly, why am I forgetting? I'll remember it in a minute. Mildred, who am I thinking of? Pasteur, yeah. He separated the crystals. Pasteur, polarized lights. I'm glad we both failed that one. Then another example that Phil points out is the following. If I take a pole and stick it as vertical as I can on the floor here, it has the full rotational symmetry of the floor. But when it falls in a particular direction, right? That's called breaking a symmetry. So when the pole falls, it breaks a symmetry and it picks a particular direction. Symmetry breaking is emergent in the sense that, so I'm going to use the term emergence. So you're either a reductionist, you're a dualist, or there's a new brand of thought that's coming up that's called emergence, which is neither. It says that there is real emergence of real things that come to exist in the universe that are real. And symmetry breaking is an example of it. Okay. Another example, which is not going to be reducible to physics and is again due to Phil Anderson, is let's think of some computer program that's computing, for example, the square root of 2. You can make the computer out of tinker toys. You can make the computer out of water buckets that pour water into one another, where there's a line on the bucket and above it is 1 and below it is 0. You can make the computer out of Pentium chips. So the computation is independent of its physical basis. I think you'll all agree. And that means that you cannot reduce the statement, the square root of 2 is computed, to any particular physics. Can you all hear it? So let me tell you what a reductionism is to an Anglo-American philosopher. Here's the idea. I've got a statement in a higher level language, And it can be replaced and is nothing but shorthand for a set of statements in the lower language, say physics. And the trick of the game is you want to have a finite set of these statements in the lower language, and if you string them together with logic, if, and, or, and stuff like that, then wherever the higher level statement is true, you can pull it out and put in this big lower level description. Everybody got it? So that's what a reduction is. It's truth preserving substitution. You can't do it for the computation because you can't finitely list all the possible ways that you could manage to compute the square root of 2 or whatever it is that I said. So the philosophers have a weaker notion called supervenance in which you get to make this list infinite. I think the view is coming to be held that that weaker level view is pointless. And it's pointless because you don't have any effective procedure for generating this infinite list. I mean, what are you supposed to say? You make Jupiter bump off Mars and 3 marbles roll down the hill and you got the square root of 2. I don't know. So you can't generate the list. So what this amounts to, and Phil Anderson is right, is that you can't reduce the computation to physics. Any specific computation is, of course, not breaking any laws in physics. It doesn't follow that you can reduce computation to physics. Now I want to move to biology. I assume everybody knows Darwin's notions, but let me repeat them. So Darwin was faced with all of this diversity of species, and he read Malthus's book in which Malthus says, gee, the amount of food you can grow increases essentially linearly, but populations increase exponentially or geometrically. Pretty soon, population's going to outrun food. Somebody's going to die. He said, so there's sort of a natural competition or a natural selection. And he needed one other idea. He needed the idea that organisms have offsprings that are different from themselves, that's called variation, and that it was heritable, it would pass on to their offspring. So it's called heritable variation. With that, we get Darwinian heritable variation and natural selection. And I can take my glasses off now because I don't have to read anything. So we get heritable variation and natural selection. Now let's ask whether or not Darwin's idea can be reduced to physics. And I'm going to say that it can't. It doesn't violate a single law of physics. Darwin doesn't tell you, nor did he know, what the physical basis was of getting offspring with heritable variation. It turns out it's us with DNA and RNA and protein and all that fancy stuff, but it could have been some other kind of goo. And life may exist on billions of planets in the universe. We have no reason whatsoever to assume that that life will all be based on DNA, RNA, and protein and be similar to Earth life. I mean, it'd be incredibly dull if it were true. And I will tell you, and I'll get there in a little bit, people have made molecular self-reproducing systems that aren't based on DNA, RNA, and protein in the standard way. That means that there's an indefinite number of alternative physics on which life can run. And Darwin's natural selection would still be true. And that means that this is called the multiple platforms argument in philosophy. It means that there's multiple physical platforms. So once again, there's no prestatable finite list of statements about our universe that you can put in place of Darwin's law, if we want to call it a law. And as a matter of fact, if you fiddled the constants of nature, there's about 23 constants in physics, and if you fiddled them a little bit, if you fiddled them a lot, you'd get really lousy universes that popped into existence and then crashed, or that also never made complex chemicals and stars. But if you fiddled them a little teeny bit, the bet is you get universes more or less like ours, in which, as far as we know, you get complex chemistry and you might get life. So we can't even say the set of universes over which Darwin's ideas would hold. That means we can't reduce Darwin's idea to physics. It doesn't contravene a single law of physics, but it's not reducible to physics. In some sense, it's a law at its own level. There's one other thing that I want to tell you about this part of not reducing biology to physics. Suppose we were to ask Mr. Darwin, we'd say, Chuck, my secretary here gave me the Chuck Darwin Chair of Theoretical Biology. I always thought Charles Darwin would be appalled at my chair. It was done with a little paint on the back of my chair, easily erased. Suppose we said, Charles, what's the function of the heart? And Darwin would say, well, the function of the heart is to pump blood. And you'd say, well, wait a minute, the heart makes heart sounds. I mean, I know, I'm a doctor. It goes lub-dub. In French, it goes lub-dub. Okay, so that already means something interesting, because Darwin would then say, yeah, but the heart wasn't selected to make heart sounds. It was selected to pump blood. It offered a selective advantage, and that's why there's hearts in the universe. I'll come back to that later. It's literally true that that's why there are hearts in the universe. Already this is interesting, because the physicist from string theory, if he could deduce, or she could deduce upward to my heart, could deduce, say, couldn't, but say, all the properties of my heart, but would have no way whatsoever to pick out pumping of blood as the function of my heart and why hearts exist in the universe. No way whatsoever. That then brings us to the question of, so once again, that says that you can't reduce biology to physics, because functions exist in biology and they don't exist in physics, because biology is that which, as Darwin told us, has been selected for. It's a real thing, selection. So we can't get that out of physics. We have to have biology. We have to have self-reproduction and heritable variation. One other thing to ask is, well, what if what the physicists could do is write down a law for the evolution of the biosphere? I'm going to show you later, stunningly, that that's not possible. At least I don't think so. Assuming that future claim of mine, suppose that what you tried to do was simulate the evolution of the universe. Well, life spans the quantum world and the classical world. So on the standard interpretation of quantum mechanics, you just know the probabilities of events. You don't know the actual happenings of events. So you'd have to run an infinite number of simulations for all the possible quantum events that have occurred in the evolution of this specific biosphere. Well, you couldn't carry out the infinite number of simulations, and if you did anyway, you couldn't know if you were right. So you can't simulate the evolution of the biosphere either. So we can't know. So once again, you can't reduce biology to physics without gainsaying any laws of physics. So biology is in this sense emergent with respect to physics, and I'm going to want to say that organisms are real in the world just as much as particles are. Now let me get to the origin. So that's sort of reductionism and the fact that it starts to fail. Okay, so now let me get, and I have a lot of material to go through, so I'll be fast about each of these, and if you want to ask me more about it later, of course I'll be glad to spend too much time on it. Let me tell you a little bit about the origin of life. One of the places where we turn to a creator God is God's hand on the Sistine Chapel with the finger reaching out to Adam's hand, and the image just glorious of God breathing life into inanimate flesh. Well, life is based, if anything else, on molecular self-reproduction. Almost all of you, if not all of you, know about the wonderful double-stranded molecule DNA, in which there's a Watson strand coiled around a Crick strand with A's and T's and C's and G's. Actually, they used to dance that way. I mean, it was really sort of embarrassing. They would dance together and kind of twine. Okay. It's not true. Anyway, it's a double helix. And this particular sequence of A's and T's and C's and G's, chemical letters on one side, specifies the letters on the other side. And Watson and Crick remark in their very first paper on the subject that the structure of the molecule suggests how it reproduces itself. Basically, you split the thing apart, and then you read the letters, and you specify the letters on the other side, and you hook them together, and there you go. So a lot of people set out, led by a wonderful chemist named Leslie Orgel, making a cousin of DNA, which is called RNA, single-stranded RNA molecules with these chemical letters, A, U, C, and G, U replacing T, and tried to make a long molecule, one single-stranded RNA that would then line up these free chemical letters called nucleotides and glue them together by the proper bonds. They're called 3', 5' phosphodiester bonds, without an enzyme. And the basic result of about 40 years' work is it should work, but it doesn't. It just doesn't. It may someday, but people are kind of giving up on it. So that doesn't work, but it may. Okay, anyway, so that's... Oh, I should tell you that I guess Stanley Miller just died, or what might have been Stanley Miller just died. He did brilliant experiments in the 1950s, and he showed that if you took an early Earth-like atmosphere with methane and stuff like that in it, and carbon dioxide, and put electric sparks in it and had some water in it, that you'd get amino acids, which are the building blocks of proteins. So we started the whole field of prebiotic chemistry, and there's been a lot of work that shows that you can get the building blocks of the molecules of life from what was supposed to be the early atmosphere. And meanwhile, there's meteorites that fall on the Earth that are called chondrocytic meteorites, and they have organic molecules in them too. So nobody knows whether or not the early complex molecules on Earth were built locally or came in from outer space during the infall that formed the planet, or both. Anyway, we had them. That doesn't give you molecular reproduction. But molecular reproduction has been achieved. I'm not going to tell you about Gunther von Kitterowski, who did it with DNA. I'm going to tell you about Reza Gadiri, who did it with proteins. And this is utterly remarkable if you're a chemist. See, DNA has this symmetry, so you can sort of see how it might copy itself. A protein is like strings on a bead, 20 kinds of beads on a long string, 20 amino acids hooked together, that then folds up in three-dimensional space to make a protein. It's not obvious how a protein can copy itself. So Reza Gadiri looked at a specific protein that coils up into what's called a helix, then folds back on itself, making what's called a coiled coil, and it's 32 amino acids long. And he said, I wonder if I took and broke a second copy into a 17 long and a 15 long pair of fragments, whether those would bind to the 32 long sequence, and then they would kind of catalyze or speed up the chemical reaction and make a peptide bond to make a second copy of the 32 amino acid long protein. Everybody got it? It worked. Anyway, it's just a big molecule that glues together two fragments of itself to make another copy of itself. Well, it works like a charm. So molecular reproduction that's not based on template replication is a done deal experimentally. So molecular reproduction does not have to be based on DNA and RNA, and that begins to suggest that life could be radically different than Earth life. Meanwhile, Reza did something else that's dear to my heart. He took a protein A and made it glue together two fragments of B to create B, then B glued together two fragments of A to make A. That's what I call a collectively autocatalytic set. Notice that no molecule in that system copies itself. The system as a whole achieves what I call catalytic closure, and the system as a whole reproduces itself. So autocatalytic sets, collectively autocatalytic sets, which I've been talking about for many, many years, is now an experimental done deal. Now, segue. Bunch of mathematics, and some stuff that I proved a long time ago. I guess I was here at Penn. Yeah, it was 1983. So I showed roughly the following, and I can explain it to you in more detail, but the bottom line is the following. If you take a complicated and diverse enough soup of chemicals, where the chemicals can undergo reactions, but can also catalyze the same reactions, then for a wide bunch of hypotheses about which molecules catalyze which reactions, you can ask, does this soup of molecules contain a set that makes itself by speeding up chemical reactions? That's catalysis. So it's collectively autocatalytic. And the mathematics says, yeah, and it's a neat story, and it's fun. But if you get a complex enough soup, all of a sudden, wham, you expect to get an autocatalytic set. That theory is now testable by making random DNA, RNA, and proteins, which is a thing that I was talking about when I was at Penn, and it's now a field in drug design, and people have shown that these random peptides fold and do all sorts of neat things, so we can test it now. There's a bunch of other approaches to the origin of life. For example, people are making soap bubble-like things out of lipids called liposomes and making them reproduce. And then there's a bunch of people who think that we started with a metabolism, and it turns out that a famous chemical cycle in you called the TCA cycle has the property that when you go around this chemical cycle, you make an extra copy of one of the molecules. So it's autocatalytic in a slightly different sense because there's no catalysis, but you get two copies. So we're making very significant progress on getting self-reproducing molecular systems. I think we've already done it. It won't be more than 50 years before we get something like that. You better confine your molecules to a small volume if you want them to interact. It'd be neat to either put them on a clay surface or inside of one of these hollow vesicle liposome things. It'd be neat to make the liposome components, hook it to a metabolism, and get it to go. We'll create self-reproducing molecular systems in the next 100 years. That will be the start, since it won't look like Earth life, of a general biology. And that's going to be just wonderful. I mean, that really will flourish. And part of what we need to think about is, are there laws for life anywhere in the universe? And that's astrobiology, which is a field that NASA is funding. So work on the origin of life is very, very promising. Now, I want to talk about agency, and I'm going to finish at about 5 after 6, because, is that okay, Gary? Will the hook come out and get me? Okay. Where did agency come from? You're all here because you think it might be interesting to listen to me, and I came all the way from Calgary because I deeply wanted to talk to you. We are all agents, we act on our own behalf, and we do things, right? Furthermore, we have values, there's meaning in our lives, we have purposes. All that's teleological talk. And philosophers have struggled with it for years. I set myself the task a number of years ago, and it's in my 3rd book, Investigations, and it's in Reinventing the Sacred, to try to ask, what's the minimum physical system about which you might be willing to stretch and apply teleological talk? And so I proposed an answer that the minimum molecular autonomous agent is a thing that reproduces itself and does a thermodynamic work cycle. So a railroad train does a thermodynamic work cycle. It's the famous Carnot cycle, named, not surprisingly, after Carnot. I won't take you through the work cycle. It's fun, but we don't have time. Anyway, it's a way of linking spontaneous processes, like a ball rolling down the hill, to non-spontaneous processes, like me pushing a ball up a hill, in such a way that you couple work and heat and you get work out of it, but a transfer of heat. It is true of all cells in all organisms that they, in general, for dividing cells, link molecular reproduction as an autocatalytic whole, by the way, it's a collectively autocatalytic system, with doing work cycles. Which leads into some interesting directions that I'm just going to hint at. First of all, work cycles don't happen at equilibrium, at chemical equilibrium. So the notion of agency is inherently a non-equilibrium concept. The second thing I want to mention, and this will be fast, I apologize. If you analyze the notion of work and you ask a physicist, what's work? I'm going to tell you something that nobody understands now, okay? And it's right in front of us. It's always the hardest thing to see, because it's right in front of you and you don't have the damn words for it. So I'm going to tell you that something is going on that Immanuel Kant was worried about 230 years ago, and he said that an organized being has an organization of a self-propagating kind that is not the mere mechanical faculty of motion. And it communicates that to its parts, though they have it not of themselves. So I want to talk about this propagating organization of process that we don't understand. I've thought about it quite a lot, and I don't understand it. But I'll at least tease you with what in the world could this thing be that's right in front of us with the following. So work is force acting through a distance. It's accelerating a hockey puck. I'm up in Canada now. It's hockey pucks. It's not baseball bats. Okay? Hockey pucks. Actually, I don't like hockey, but it's hockey pucks. So there's a guy named Atkins who wrote a book on the second law of thermodynamics, and he says, work's more than that. It's a thing, said Atkins. Work is the constrained release of energy into what the physicists call a few degrees of freedom. Degrees of freedom are things that can change, like the directions that particles are moving or something like that. So an example is a cylinder and a piston and the working gas exploding and pushing the piston down. So the bouncing molecules in the piston head, the head of the cylinder, the energy in that is released in the what's called translational motion of the piston down the cylinder, so into a few degrees of freedom. You can all see that intuitively, right? So that's work. Now I'm going to ask two new questions. First of all, one's an old question. What are the constraints? Well, it's the cylinder and the piston. I mean, even I understand that. Now, what the physicists do at this point, and there are physicists in the room probably, is they cheat. They mathematically put in what are called boundary conditions and solve the whole thing. But that's not what happened in the real world. What happened in the real world is the following. Where do the constraints come from? Well, it took work to make the constraints. It took work to make the cylinder and the piston and to assemble it all, right? So we get to a very funny puzzle that's the start of being puzzled. It takes work to make constraints, and it takes constraints on the release of energy to make work. And that's nowhere in the physics books. It's right in front of us. And I will say this part fast by saying cells do this. They do work to construct constraints on the release of energy, which when released does lots of things, including making more constraints on the release of energy, which does lots of things, including making more constraints on the release of energy, and it all propagates around in the cell until a bunch of tasks are achieved, and you achieve a closure in a space of tasks that we don't know how to describe, and the cell reproduces itself. That's what I mean by propagating organization of process. I think there's fundamental new mathematics to be done here. I mean, Herm, who's a dear friend, is sitting in the front row. Maybe it's not fundamental new mathematics, but we don't have it. The closest we can come to it is something like a river in a riverbed, where the riverbed constrains the flow of the river, but the river changes the shape of the riverbed by erosion. Well, we can come closer than that. There's something called Ricci flows in general relativity that could conceivably be of some help here, but I don't know. I don't know general relativity. Anyway, propagating organization of processes is something that cells do, that we're missing, and it's come to exist in the universe. Let me go back to agency. For a bacterium swimming up a glucose gradient, a molecule of glucose is a sign of glucose actually, a local gradient of glucose is a sign more glucose that way. And the bacterium swimming up the gradient is interpreting the sign and going to get that food to get dinner or lunch or brunch. And so in the Peircean sense, that's semiotic, and that's meaning. And it's assembled by natural selection. That machinery wouldn't be in the cell unless natural selection had done its job, right? It's to the advantage of the bacterium to swim up the glucose gradient. That's why the whole thing's been assembled. But we can't reduce natural selection to physics, so we can't reduce the semiotics, and therefore the meaning, and therefore the value to physics. But that doesn't mean that the meaning and the value, without attributing consciousness yet, isn't there for the bacterium. So I think that with agency comes meaning and value and doing. You see, when you do something, it's not everything that happens, it's a subset of the things that happens that are the doing. It's a swimming up the glucose gradient. It's not the way some water molecule happens to wiggle on your flagellum. And when you go to the store, you go to the store, and it doesn't matter if you had to go around the block, right? So there's this big difference in description between the physical description and the description that we use for doings and actions. So I want to say that doings and actions and meanings and values are emergent in the real universe. And we're living examples of it. I've got 10 minutes, and I want to get to what I think is the most astonishing part of all of this. And to do so, I have to tell you what a Darwinian pre-adaptation is. So I've already told you a Darwinian adaptation. It's the pumping of blood. Well, I have to tell you one other thing first. And it's to tell you that the universe is vastly non-repeating. And what I mean is this. Think of a protein with 200 amino acids on it. So it's 200, and there's 20 possible amino acids. So how many proteins are there length 200? Well, 20 in the first position, 20 choices in the second position, and so on for 200 positions. So it's 20 times 20 times 20 times 20, 200 times, which is 20 to the 200th power, which is about 10 to the 260th power. Now there's about 10 to the 80th particles in the known universe. The universe is about 10 to the 17th seconds old. If all of the particles in the universe were acting on a 10 to the minus 15th or femtosecond timescale to do nothing but make proteins length 200, it turns out it would take 10 to the 67th repetitions of the history of the universe to make all possible proteins length 200 once. Now the fastest timescale in the universe is the Planck timescale, 10 to the minus 43rd seconds. If you substitute that, then it would only take 10 to the 39th repetitions of the history of the universe, okay, to make all possible proteins once. This means something physical and utterly fundamental. It means that at levels of complexity above the atom, where we do have all of them, not in equilibrium, but we do have all of them, the universe is on a unique trajectory. It will never make all possible proteins, all possible bacteria, all possible people, all possible operas. Wendy's just written a new one. That's proof that there's at least one that has, right? And by induction, there's a bunch more, okay? All possible Chevrolets. This is stunning to realize because with this, history enters the universe. Because the space of the possible is vast compared to what the actual can ever be. So for the physicist, the word for this is that the universe is grotesquely non-repeating or non-ergodic. We're on a unique trajectory. And that means that when the heart arises in the biosphere, it's a unique event and a unique structure that came to be. So it's not that the heart disobeys any laws of physics, but it is the organization of the heart that allows it to pump blood, the structure and the propagating process, and that the physicist cannot give us. Doesn't break any laws of physics, but the physicist can't get there. It's emergent. Hearts are real, and you're alive because of it. Okay, so now it's the Darwinian pre-adaptation. So Darwin had a really neat idea. He said, you know what? A causal property of, say, your heart that's of no functional significance in the present environment might be of interest and of use in some different environment, like your heart sounds. So your heart is pre-adapted without any design to have this useful new property in this new environment. Did everybody hear the words? Okay, so let me give you an example. I had it backwards. There's an organ called a swim bladder and lungs. And I thought lungs evolved from swim bladders, but Gunther Wagner said, you fool, it's the other way around. And I said, okay. So here's what the paleontologists say. There are in fact lungfish that, as you can surmise, have lungs in them. The swim bladder is a sac in certain fish, partially filled with air and partially with water, that adjusts neutral buoyancy in the water column. So here's how it is thought, or known, that swim bladders arose. There were some lungfish, and they were in some water without much air. The lungs arise as sacs off of your gut, and so the fish swallowed some of this air-poor water. Some of it got into the lungs, made some bubbles, and the fish survived better. And now you had a sac with air and water in it. It's on its way to being a swim bladder. It's pre-adapted to becoming a swim bladder. So that's what a pre-adaptation is. So, first, some easy things. Notice that a new function arose in the biosphere, adjusting neutral buoyancy in the water column. Anybody disagree? Okay, good. Did it have causal consequences in the non-ergodic evolution of the universe? Yeah, new species, new proteins evolved. It had causal consequences. And now I'm going to ask the central question. Does anybody in the room think that you could say ahead of time what all possible Darwinian pre-adaptations are for all organisms alive now, or say just for human beings? Does anybody think so? I've never found anybody who thinks so. I don't know how to prove it. I don't know whether I'm making a mathematical statement or a statement about the world, but I think it's true. And I think part of the problem is obviously this. We have no way whatsoever that I can think of to list all possible selective environments. How would we list them? What would we do to list them? I'm going to say some things and then tell you the physicist's criticism. So what I want to say is that we don't know ahead of time, we honestly don't know ahead of time that swim bladders will emerge, or other Darwinian pre-adaptations which are abundant in evolution. We don't know. Not that it's a matter of, we could have guessed. It's that we really don't know. In principle, we don't know. We have no idea that this will happen. The next thing I want to say is radical. I'm going to say one of the more radical things you've ever heard. What's a natural law, like Newton's law? Murray Gell-Mann, Nobel laureate, not very friendly friend at the Santa Fe Institute. Murray's incredibly smart, but he's not the easiest guy to get along with. Says, and I think accurately, first of all, that a law is a description. It doesn't guide the universe, it describes the universe. And then he says, I think rightly, a law is a compact description of the regularities of what's happening. Okay? Like Newton's laws. Could you have a law to describe ahead of time, it's a description ahead of time, the emergence of swim bladders? And I think you'll all agree that the answer is no. You couldn't have a law to describe the emergence of swim bladders. It doesn't mean that it's not causal. Let me call it causally anomalous. There's perfectly good causes. It's just that we can only figure them out after the fact. But we couldn't have a law for it. And that means something fundamentally important. It means that we are in a universe that is not only emergent, it's creative. Not in the sense that there's a creative agency, it's simply creative. It's doing things that we can't know beforehand. Okay? It turns out you can't even make probability statements about this, and I don't have time to tell you about that. But the two standard interpretations of probability theory are the frequency interpretation and Laplace's interpretation, and neither of them work. We can't even make probability statements. So we're confronted by the fact that you've not thought about, that in the evolution of the biosphere things arise that we can't say ahead of time. And mathematicians don't have a way to mathematize it, because if you think of general relativity or Newtonian mechanics or quantum mechanics, you know ahead of time what the space of possibilities is, the state space. You don't know it for the evolution of the biosphere. Now let me say that the same thing is true in human economy and human culture. And then I've got a few minutes to come to a close. So I'm going to tell you what's supposed to be a true story about the invention of the tractor. So this, of course, took place in Texas, because the only place that you can tell jokes about is Texas. And even that's getting politically dangerous for obvious reasons. So there were these Texas engineers, and they thought, let's make us a tractor. They thought, we're going to need one big engine block. Well, let's go get a big engine block. They got themselves a big engine block, and they put it on a chassis, and it crushed the chassis. Well, I said, that's simple, we'll get a bigger chassis. And they got a bigger chassis, and they put it on and crushed the next chassis. So they kept getting bigger and bigger and bigger and bigger chassis, and the engine block kept breaking all the chassis. Finally, one of the engineers says, you know, the engine block itself is so big and rigid, we can use the engine block itself as the chassis and hang everything off the engine block. And that's how tractors are made. And Formula racing cars used to be made. That's a Darwinian pre-adaptation. It's an unused causal consequence of the engine block, namely its rigidity, for a novel function, right? The evolution of the economy is not solely, but largely governed by Darwinian pre-adaptations. I just have fun in the book with screwdrivers. Try to name all the uses of screwdrivers. I mean, you screw in screws, you open cans with them, you can prop open a window, you can stab an assailant, you can put it on the end of a stick and go fishing, you can use it to chop down a coconut tree when you're cast away on an island. Is there any finite list of what you can use? It's an object d'art. It's probably a literary thing too, I don't know. But it certainly is an object of art. Okay, so is there any list that you can prescribe for all the uses of a screwdriver? Well, no. I think this means lots of things. First of all, I think that it means that the evolution of the economy in general cannot be prestated. Practical example. In fact, about 10 years ago, Bell South came to me when I was at the Santa Fe Institute, and they asked me to consult on whether or not they should put billions of dollars into fiber optic cables. And I thought, they're paying me $10,000 a day. I actually don't have the faintest idea. But I'll lie, you know what I mean? So what honest to gosh happened is that, you know, we talked all day and I was listening in fiber optic cables. Then finally at the end of the day, having no idea what to say that might sound like I had a brain in my head, I said, well, what if some kid learns how to keep tin cans up in the air with BB guns and bounce signals around the world? What's going to happen to your fiber optic cables? And they looked at me and they paid me my $10,000 or whatever it was and went away and invested billions of dollars in fiber optic cables. And 7 years later, people learned how to bounce signals off of satellites and they lost billions of dollars. Were they stupid? No. Did they know that there were going to be that there were going to be satellites and bouncing signals around the planet? No. The evolution of the economy cannot entirely be foretold. This is a huge subject because the reigning theory in economics presumes that you can prestate all possible what are called dated contingent goods. You can't. We've come from 100 goods and services in the global economy 50,000 years ago to maybe 10 billion now, and we don't have a theory for this explosion in diversity, and it's what's driving economic growth, let alone the hell that's coming as we confront what we're confronting. So I'm going to finish up with the following. What this says is that I think, honest to gosh, really for true, the reductionist worldview is inadequate. Not stupid. We've done brilliant science with the reductionist worldview. But it doesn't cover what I've talked about. I think it means two enormous things, and then several more enormous things. First, we live in an emergent universe. Organisms are real, so are particles, but so are organisms, and so are hearts. Second, we live in a ceaselessly creative universe, without there being a creator agent. It is ceaselessly creative, non-ergodic, all around us, all the time, in this conversation, in this talk, and what we will say when I finish in a few minutes. We have no idea what we're going to say to one another. It'll be fun, but we don't know what it's going to be. We live in a ceaselessly emergent creative universe. Now, what I want to do is, I want to say, we have a choice whether we will use the God word. God is the most powerful symbol humanity has ever created. I want to steal it on purpose, but with history on my side. Notre Dame is built on the ruins of a Druid holy site. When the Spaniards conquered the Incas were carrying stones to the tops of mountains to worship their sun god. And the Spaniards, being reasonably bright about these things in the time of the Inquisition, said, "Why don't you chaps build crosses on the tops of the mountains and carry the stones up to the base of the cross?" Which is what the Incas did, and pretty soon they were worshipping the cross rather than the sun god. We always build our new churches on the holy sites of the other. How many gods has humanity had in the last 5 million years or 100,000 years? Thousands. Okay? I want to take the God word on purpose, but with reverence, genuinely, and use it to mean precisely the creativity in the universe, the natural universe, the one that we're living in, the one that we're creating all around us. This abundant, amazing, miraculous place where all that's happened is that the sun's been shining for 3.8 billion years, and walk outside and look, and if you're not stunned, you're stupid. Okay? Now, suppose we do that. Many people in this room believe in the Abrahamic God. Science is never going to prove you wrong. And I wouldn't for a moment say you shouldn't have that belief. So I want to say, first of all, to us secular humanists, if we can adopt as our sense of God, one sense of God, the creativity in the universe, we can find solace, meaning, and a way to orient our lives as men and women in this world with this reality around us. And it ends the battle between faith and reason. There is no battle between faith and reason. It is the real universe, and we're members of it and making it together. If you believe in a deistic God who set the universe up, as people thought in the Enlightenment, and let it go, you can say, "Thank you, God, and what an amazing universe you made. It's creative on all of these ways," and you can cherish that as well. And if you believe in a theistic God, which I am sure many of you do, I don't. I wish I could. I'm getting old. I mean, I would like to believe that I was going to heaven. It's not in the Jewish tradition. We just die. I mean, it's terrible. But you can say the following to yourself: I still believe in the Creator God who will answer my prayers, and if you believe that, God bless you. But when God is not working miracles in the world and answering your prayers, it's still the universe that God created that's miraculous in its creativity, and you can cherish that and find hope and meaning in that. Does that mean that everything that happens is good? Of course not. We'd love to kill one another. The chapter in my book is called Broken Bones. Do evil things happen? You bet. Now let's come to the sacred. All of our gods over all of these years have told us what is sacred. It's written in the Quran, it's written in the Bible, it's written in the Old Testament. Do we need a God to have a sense of sacred? Well, the Buddhists don't. Anyway, it was we who invented God. Now, that may rub some people wrong, but there's been a lot of gods, so if yours is right, what did everybody else do? So it's we who have told our gods what is sacred, and they have told us back what we told them. Then it's always been us talking to ourselves. Why not take on the possibility at this stage in the evolution of human culture that we should jointly choose what we will hold to be sacred? Does that make it not sacred? Of course not. It's always been us who chose it. It's that which we hold to be most valuable. Does that mean it will never change? Of course not. The Ten Commandments says, "Thou shalt not steal." Stealing meant one Israelite shouldn't steal his neighboring Israelites' slaves. Would we hold that to be sacred now? Of course not. Slavery is appalling. So our sense of the sacred evolves. And this means something that I think that we have to get our heads around. And I want to turn to British common law and then end with just a couple more comments. British common law is wondrous in that it is the congealed morality of a people over 700 or 800 years dealing with concrete moral problems and concrete situations. Not only is it wise, it's also evolved a wise way of evolving. In other words, it has its own orderly way of changing. It's called precedent in changing precedents, some of which ricochet through the law and some of which never matter. It's not impossible for human beings to construct ways of having traditions that are wise and settled and to be revered, but yet are malleable and can change. And law is an example of it. I think we need to do that. So I think we need a sacred, I think we need a sense of God. I think from that, almost inevitably, one comes to a sense of what is sacred, and at least some of it seems clear to me. Life is sacred. All of life is sacred. The trees across the river from my house in Bragg Creek in Alberta are sacred. I can cut them down if I want to, but I better have a damn good reason to do that. That's God's work. And I could change the river, but I better not. It's God's work. I can if I want to, and I don't mean a supernatural God. I mean the universe. I better have a good reason to monkey around with nature. Okay? So I think we need a sense of the sacred. Out of that, I hope we can collectively construct a global ethic. I think we need a new sense of Eden, not the one we left, the one we can go towards. I don't know what it is. I know little pieces of it. It's not up to me to invent, but I think we have to call for it. I think we have to try to create it. Out of that will come a sense of, to the extent that we can have any effect on shaping a global civilization, which is only partial with all of the things I started with, like global warming and peak oil and water and desires to kill one another, we can help shape what it will become. In other words, it's time for us to see ourselves to end in an emergent, creative universe of spectacular, enormous diversity, magnificence, in which we can find reverence and awe and meaning, and in which we can find orientation to live our lives and build a civilization that we can choose, even though we do evil all the time. Thanks.